All right, so I decided to make a quick little video for you guys. I guess it might not be that quick, but we're gonna look at some of the problems that we did not cover in class so you can kind of help you review a little bit, okay? So, looking at number 15, so we kind of check that one out again. So we have an inclined plane problem here. Okay, so there's our inclined plane. Yeah, it's probably a little bit too much of an incline. Okay, so we are at a 42-degree incline. And we have, reading the stuff, we have coefficient of friction. The genes on the incline was 0.650. Again, we have our 42-degree incline. So it doesn't seem like we have a lot of information. We don't have how much the guy weighs. Hopefully you remember from class that that doesn't really matter that much. Okay, so let's write out our equations. So normally we have something like this, where it's net force equals applied force minus friction. Well, since he's going down, our slope is not applied force anymore. This one's going to be our gravitational force. Okay, so it's Fgx minus force of friction. So we have to write out what force of friction is. The force of friction equals mu times normal force, and then we got to write out what normal force is. So that way we can kind of plug everything in. So normal force is going to be mass times gravity, and if we declare our axis, so positive y, oops, we got to go down the incline here. Okay, there's a little guy. So positive y is that way, and we have positive x being that way. So that means we want our normal force to be positive and gravity is negative. So we need to have that normal force be negative mass times gravity. Okay. And then obviously once you plug in gravity, so g is our 9.8. If we say it's a negative 9.8 meters per second squared, that will take care of that, and our normal force will be positive when we plug it in. Alrighty, so then we need, so we took some time to draw our free body diagram in class on this one. So we had Fgy, force of gravity, that one should probably be a little bit longer. Fgx going that way. And we had our normal force going up from the surface, and then we had friction keeping him, or slowing him down a little bit. Okay, so this 42-degree angle is also right in here. So then, if we want this x component of gravity, it's also this part right there. So to get that component, so Fgx, we need sine. So it's going to be Fg, which is just mass times gravity, sine of theta, Fgy. So that's going to be mass times gravity again, cosine theta. Okay, and we need this because that's what balances out normal force. If we look at those two forces, they're in the same plane, opposite directions. So my normal force is equivalent to my mass times gravity, but in this case it's going to be the y component of that. Okay, so really this should be negative Fgy. And then that gets plugged into there. And remember, gravity is negative, so that'll end up canceling itself out. So let's put everything into our equation. So net force equals my x component, so that's mg sine theta, all right, minus friction, so it's mu normal force, which is mu Fgy, and we know Fgy is that, so it's minus mu mg cosine theta. So rather than trying to keep track of all the signs and stuff in here, we know that we can just say that that's going to be our gravitational force, which is this one. So that's going to be moving us in a positive direction, and friction will be taking away from that movement. Okay, so net force is mass times acceleration. Let's put all that stuff in there. And then remember, our masses will cancel out. We don't need them. And then we can figure out our acceleration here. So that's going to be 9.8 times sine 42 degrees minus mu, which is 0.650, times gravity, which is 9.8, times cosine 42 degrees. All right, we punch that in our calculator. So 9.8 sine 42 minus 0.650 times 9.8 times cosine 42. And we get an acceleration of 1.82. And that's meters per second squared. Is that what we were looking for? Yes. So from there, we could use that in our kinematic equations to figure out anything else we need. All right, so let's try 16. So steep water slide, occupants in the boat falling from a height of 100 feet down a ramp that makes a 45-degree angle with the horizontal. Okay, so we have, let's just say this is our water slide. So it's 100 feet up, and we have a 45-degree angle with the horizontal. And let's say we got these guys and they're on an inner tube or something up there. All right, consider the mass of the boat and its occupants to be 1,500 kilograms. And we'll see if we need that or not. Coefficient between the boat and the ramp. Oh, we're on a boat. Let's change that to a boat. Okay. Coefficient of friction, that's mu, is 0.10. Determine the frictional force, the acceleration, and the distance traveled along the incline, and the final velocity of the boat at the bottom of the incline. Begin with a free body diagram. So free body diagram is going to look like this again. Okay, but instead of this, we're going to have a 45-degree angle. We also need to use, so we can kind of assume that this is a right triangle. If we want to, we can kind of figure out that distance of the ramp. Okay, so we have 100 feet up. Let's see if we can just use sine to figure out our distance of that ramp. Okay, we also need to convert that to meters. So we're going to have to divide 100 by 3.28. So we're 30.48 meters. And if we want to figure out that hypotenuse there, let's see if we can just use sine to get that. So we want sine of 45 degrees equals 30.48 meters over, let's just call it x for our hypotenuse. So we're going to have to take 30.48 divided by sine of 45. And we get 43.11. So that ramp, approximately 43.116. So we'll just say 12 meters. So that's how long the ramp is. We're going to need that for later so we can find velocities and such at the bottom of the incline. Okay, so now, just like this problem before, we're going to figure out our acceleration. So we don't have to do all the work here. Everything is exactly the same. So let's jump to this equation right here and use that down here. So A equals G sine theta minus G cosine theta. Oop, we need that little mu in there. And then let's plug it in. 9.8 sine 45 minus, so it's only 0.10 now, times 9.8, almost missed that. 9.8 cosine 45. So let's put that in our calculator, see what we get. So sine 45 minus 0.1 times 9.8 times cosine 45. And I have 6.24 meters per second squared. So that's our acceleration down the ramp. So we found that, and actually I needed to determine the frictional force. which is, we need force of friction. So that's going to be this equation up here, mu times normal force. And remember that our normal force is going to be the y component of gravity right there. So that's mg cosine theta. All right, so let's just plug stuff in there just because we want another answer off to the side apparently. Times our mass, which is 1500, times gravity, which is 9.8. And then we got cosine 45 degrees. So then we put that in our calculator. 0.1 times 1500 times 9.8 times cosine 45. So frictional force is 1039.45 newtons. So, and we could say that that is a negative because that is going to be working against our boat there. Okay. And now you might be wondering, why is that so massive? Well, that's massive because we put that weight of the boat in there this time. If we're just finding the force of friction, the masses canceled out up there, so we didn't really need them. But if you're actually finding that force of friction, you're going to have to put the mass in there. Okay? So distance traveled along the incline, that's this. So that's just our distance of the incline. So we have a delta x, we have an acceleration, we have a force of friction, and we need the final velocity at the bottom of the boat. Okay, so then we're probably going to have to use, we can say our initial velocity is 0, because more than likely they're starting from 0 up at the top. And let's say we need this equation. Okay, so we need final velocity, what we're looking for. Initial velocity is 0, so let's plug stuff in. 2 times my acceleration, 6.24 meters per second squared, times my delta x, which is 43.12 meters. And then we're going to have to square root all that at the end here to actually get our final velocity. So 2 times 6.24 times 43.12. Okay, and then we want to square root that answer. And I have 23.197, so about 23.2 meters per second. So that's how fast they're going at the bottom of the ramp. Okay, so let's look at the next couple down here at the bottom. So we have projectile motion here, and we have a hammer throw, which is centripetal force. So our centripetal force, are we looking for? So it says, what's the tension on the chain? All right, so what balances out tension is our centripetal force. So this is our centripetal force, and that's tension. So really, those are balanced because that hammer is not flying off into space. So we need to find centripetal force. Okay, and we also need centripetal acceleration. And yes, I know I'm skipping 17, but 18 is a little bit easier. So centripetal force is mv squared over r. Okay, it's also mass. So mass has to be in there in order for it to be a force. 4 pi squared r over t. Okay, so that's the force. If we want just centripetal acceleration, that's these two things again without the m. So v squared over r, and it's also 4 pi squared r over t. Okay, so t is the period, which is how long for one rotation? And do we have that? Yes. So we have everything here. Let's find our centripetal acceleration first, then just take it times our mass, and we'll have our centripetal force. Okay. So plug everything in. So centripetal acceleration is going to be So we have some easy numbers. So we got a radius there, we got a mass, we got a period. So it looks like we're probably going to be using this one. We don't technically have a velocity. So 4 pi squared radius 1.8 meters over period, which is 1.0 second. Plug that in your calculator. So 4 pi squared times 1.8 divided by 1. Probably didn't need my calculator for that, but it's 71.06. And that's meters per second squared. Okay, that's my centripetal acceleration. So tension, again, tension is equal to centripetal force. And centripetal force, the only thing I have to do is take mass times acceleration. So if I take a mass and I multiply it by this, then I will get my centripetal force. So I'm just going to take that number times 7. And I get 497.43. And the forces are in newtons. So that is that. All right, so let's take care of this dart problem, and then we'll call this video a wrap. So dart player throws a dart horizontally at 12.4 meters per second. So remember, with projectile motion problems, we can do our little dart guy. Okay. And he hits the dartboard 0.32 meters below from the height which it was thrown. So dartboard, maybe it's on the ground or something. But that is 0.32 meters. Okay, how far away is the player from the board? So we are looking for this, which is delta x. Okay, we know our initial velocity. In this case, it's a horizontal velocity. Okay, so he's throwing it straight horizontally. The only thing it's working on is gravity. So let's say that that's v sub x, because horizontal is independent from the vertical on these. All right. And if we talk about acceleration in the x direction, there is 0 meters per second squared acceleration. So we really don't even need to write it. All right, let's think about the y direction. So acceleration in the y. And since this is just going straight down, let's say that that's going to be my positive y, and that's my positive x. So let's say acceleration is 9.8 meters per second squared. Let's keep it positive just for the sake of making things nice. And we have this displacement here, so that's my delta y. We have a displacement in the y direction, which is 0.32 meters. All right. So from there, we can start to use some of our kinematic equations to solve this. Okay, so let's think about equations that we have. Let's use our y values first. So we got delta y equals initial velocity times time plus 1/2 acceleration times time squared. And I chose this equation because time is in here. And I have everything that I can solve for time. Time is the shared thing that you want to solve for on projectile motion problems. So you always start by using what you have in the y direction and solve for time. Okay? Initial velocity in the y direction. So it's starting from up here, and then it's dropping, but our initial velocity is going to be 0 meters per second. Forgot to write that down. That's nice because that takes that out of the equation. So delta y is 0.32 meters. And then we have 1/2 times 9.8 t squared. So 0.32 meters. Half of 9.8 is 4.9. Okay, so we're going to divide by 4.9 and then square root that. Okay, let's just do that all at once here. And then we end up with, let's see what we got. So 0.32 meters divided by 4.9. We want to square root that. And I get 0.26. So that dart is in the air for 0.26 seconds. Okay? So now that I have time, I can use this component. We have Velocity equals distance over time. And since we're using distance in the x direction, I have to use velocity in the x direction. So this is kind of an easier equation that we've used for projectile motion. Okay, we got that 12.4 meters per second right there. So that's its initial x velocity. That does not change. So 12.4 meters per second equals delta x, which we don't know, we're trying to find, divided by 0.26 seconds. So multiply the 0.26 out of the bottom. Gone. And we get delta x equals, so let's take that times 12.4. And I kept the answer in my calculator. I got like 0.255555 just for the sake of if you were off a little bit. So I got 3.17 meters. Okay, so this is just video 1. If I get some time, I'll make video 2 going over some of these other ones on the back. Okay. But hopefully that helps you guys out. You can kind of go back and forth on the video if you needed to see something again. So good luck.